All right, so this washer method, here is kind of the diagram of what is happening. We have this shape here that is 2D, okay? And for this one, we're gonna rotate it about the x-axis. Oops. Rotate it about the x-axis. And if I do that, I'm gonna have some sort of, okay, don't judge my art ability here, but this curved shape looking thing here. That's not great, but that's okay. And it would be 3D. So I'm gonna have this like cylindrical thing all the way around, right? But then on the inside, we're gonna have this like hollow space, right? So we're gonna take the area of the whole thing, we're squaring that and we're integrating it so that way we can find the volume. And then we're gonna subtract the whole without the h on the inside to figure out what the volume is of just that region that is rotated about the y-axis, or sorry, the x-axis. Okay, a little hard to see, but can we kind of visualize what's going on there, bringing it out and around all the way, and then you're gonna have that hole on the inside. The only difference between these two formulas here is this is your horizontal and this is your vertical. So if I would rotate it along the y-axis, so we're rotating it this way, for this picture that we've got, if this is my shaded region, that would look something like this. And then I would have my, something like that with my inside area there subtracted. Okay, so again, it's your whole area squared minus your whole with an h squared. Okay, our formula is the exact same as your disk method. We're still squaring whatever that radius or whatever that r value is, but the only difference is that you're going to have to subtract those two things so that way only get the space that's rotated about. Okay, we don't want that empty space to be accounted for. Does that make sense? Okay, all right, let's look at an example. Okay, we're going to use basically the same picture every single time, but we're going to do different rotations with respect to different axes. Okay, so this one we actually I lied. There's going to be two different graphs that we're going to look at. So for this one, we're finding the volume that is shaded with the region square root of x and x squared, and we're rotating it about the x-axis. So let's go ahead and graph these two things. So square root of x starts at 0, goes to the point 1, 1 if you forget, and it looks something like that, right? X squared, seen that for a long time here. Again, starts at 0, 0, goes through 1, 0, but it is going to be concave up. So it looks something like that. So the region that is bounded between those two curves, we are going to rotate about the x-axis. So I'm going to go ahead and draw a dashed line here. Actually, oops. And then I'm going to rotate about the x-axis. Okay? So these representative rectangles are going to be super helpful in figuring out what is big R and what is little r. Okay? So I would choose your two favorite colors and then just use those consistently across these all of these examples. Okay? I'm going to use pink and blue. No, pink and green. We'll do pink and green. Okay? So if I want to find my big R is always the farthest curve to your line that is being rotated about, okay? So that would be from the blue line all the way down to that black dashed line, okay? So it's going to look something like this. This is my big R rectangle. That is my big R of x. Okay, so that would be like the whole with the W. This is your whole volume that we're going to find. And then we're going to subtract the whole with an H. Okay, so that would be this distance between the red curve and the black line. That's my little r of x. All right, so we've got to figure out what the expression is going to be for the big R of x. So big R of x is going to be my blue curve minus the line that I'm going to. So my big curve, or my blue curve, sorry, is the square root of x, and then minus 0. Well, the square root of x minus 0 is just the square root of x, right? That's that distance between. No matter where you are in between the shaded region, it's always going to be the square root of x minus 0. Okay, little r of x is going to be using the red curve. That's my top curve. So my red curve is the x squared, so I'm taking x squared and subtracting 0, which is just x squared. Okay, so if I plug this into my formula for volume of a washer is pi times the integral from a to b of big R of x squared minus little r of x squared dx. Now, it would change if it was in respect to y's, but we are in respect to x this time, and a good way to double check is whatever your rectangle is being perpendicular to, that is what you are integrating with respect to. So we're perpendicular to the x-axis or something that is parallel with the x-axis, okay? So we are going to be integrating with respect to x. If I drew my rectangles horizontally, I would integrate with respect to y, okay? So let's go ahead and plug in our values. So I've got pi times the integral of the square root of x squared minus x squared squared. Okay, and we're starting at 0 and we're going to where? Where's my x value going to for that shaded region? 1. So I'm starting at 0 and I'm going to 1. Okay. On your test, you're not going to have to do like 10 of these problems, right? But you might have to, what was I going to say? You might have to like show just the setup, or it might be like simplified a little bit and then you just have to select the right one. So you don't have to like do the full math and do the integration. But so for some of these we'll do the integration, some of these I'll just tell you the answer to save us some time, because this integration isn't too bad, especially once we simplify this, because the square root of x squared, that's just x, right? And then x to the second would be x to the 4th. Okay. Now that's not a bad one. We would just integrate these two pieces separately. So it'd be x squared over 2 minus x to the 5th over 5, and we could evaluate that at 1 and 0. But to save us the time, this is really the new piece that you need to know. Your answer would be 16, no, that's not it. That's not your answer. What is your answer? 3 over 10 pi, or 0.3 pi, okay? Or whatever 0.3 times pi is actually. But if you plug in this integral right here, the integral from 0 to 1 of x minus x squared dx, you should get 0.3, and then you'll have a pi symbol in front of that, okay? Okay. This one we're finding the volume, shaded region in between these 4 lines and a curve, and then we are rotating it about the y-axis. So let's go ahead and graph these on our graph, and then this is the same picture we're going to use for the next, I think 3 examples, okay? So go ahead and graph x squared plus 1, y equals 0, x equals 0, and x equals 1 on your graph, and find where your shaded region is. The region that is being rotated, what color do I want to use? Let's use yellow. This region right here is being rotated about the y-axis, okay? So when I'm going to draw in my representative rectangles this time, I'm going to draw them perpendicular to the line that we are rotating it about. So are my lines going to be horizontal or vertical? Horizontal, right? So I'm going to draw in my big R of x goes from the farthest curve to the line that we're rotating it about. So this right here will be my big R of x. And then, where's my little r of x? The parabola thing, right? So there's also one more piece. If you guys go back to this bold part here, see how it says two integral case? Similar to how I was showing you the problem up on the board here from the homework from last time, we're going to have to do this in two separate pieces. So the first piece that we're going to look at is from 0 to 1. That's going to be my volume 1, I'm going to call it, because technically, do I have any like hole that's in the middle that I need to cross out there? No, that's actually a disk. So volume 1 is going to be just a disk. We don't need to separate or subtract anything, okay? Now this up here, we'll call volume 2. This is going to be a washer that you are going to have to subtract the inside of, okay? Now the nice thing is that my r of x value is always going to be the same no matter which one it's in, right? Whether it's in the volume 2 section or in the volume 1 section, that's still r of x, right? So my big r of x is your distance farthest, or farthest right, I should say, and then 2. Oh, yes, good call. These are y's. I meant to write that, and I didn't. This should be in terms of y. Thank you. Because we are perpendicular to the y-axis, so we are not integrating in terms of x this time, okay? So r of y is going to be this value 1 subtracted by 0. It's just the distance between, right? So 1 minus 0 is just 1. Okay, this little r of y is a little bit more complicated because my curve here that I drew in red, the formula for that was y equals x squared plus 1, right? But I want it in terms of y. So what do I need to solve this equation for? Y. Oh, wait, no. It's already solved for y. I need to solve it for x, right? So if I solve this for x, I get y minus 1 equals x squared. So then x is going to equal the square root of y minus 1. And technically, yes, it's plus or minus, but I only care about the right-hand side, so I don't need to have the negative in there, okay? So for your r of y formula, that's going to be the square root of y minus 1. And then we're going to the line x equals 0, so it's minus 0. So your r of y is just the square root of y minus 1. Okay, are we okay with those two values? Big R of y, little r of y. Okay, so now I can find the volume of these two pieces individually, and then we can just add these two things together, okay? So my volume 1, so my disk, is just going to be pi times the integral of 1 squared dy. Because there is no subtraction needed because it's a disk, right? Now what are we going to and starting at? We're starting where?
1.
We're starting here at 0. And then we're going up to 1, right? So my integral is going to evaluate from 0 to 1. And that's a pretty easy one to do by hand, so let's go ahead and do that. That would become pi times x evaluated at 1 and 0. So your volume there is just going to be pi, right? So that's your volume 1. Volume 2 is my washer, so I am going to have my pi in front times the integral of big R squared, so that would be 1 squared, and then minus my little r squared, so minus the square root of y minus 1 squared dy. Big R squared minus little r squared. And then where am I starting and where am I ending? Are we also starting at 0? No, where are we starting? At 1 and going up to 2. So we're going from 1 to 2. Okay, the nice thing about that squared piece there is it's going to get rid of my square root. So if I simplify this a little bit, I would get 1 minus y minus 1. Do we agree? Do we agree? Someone should not agree with me for what I have up there. Because I need to have a parentheses around this, right? If that's going to be true. Otherwise, I need to distribute that -1, right? So be careful with that. This would give me actually 1 minus a -1, which is 2. minus y dy. Okay, and again, to save us some time, because the setup of these is really the hard part, from here we can integrate this by hand, or we can use a calculator. If we integrate this by hand, you actually end up getting just pi over 2 for your volume 2. So that means that my total volume is just pi plus pi over 2, which is 3 pi over 2. Okay, this is one we were just going to set up, but we're not actually going to solve it. So we're bounded by the same curves and same lines again. So I'm going to go ahead and shade in that region that we are going to rotate. So it's that same region. And it is going to rotate this time around the line x equals 1. Nope, I lied. It's x equals negative 1 that we're rotating it about. Okay, so x equals negative 1 is going to be over on the left here, this thing right there. So I'm going to rotate that shaded region about that line. Okay. Now, this one's very similar to the previous problem in the sense that when I draw in my horizontal lines, right? This down here from 0 to 1, is there anything, well, actually, no, that's a lie. I'm subtracting something, right? I'm subtracting this area right here. But then once I get up past 1, do you see how that distance that's going away is changing each time? So we're going to have to find the volume, not just once, but twice. Again, splitting this up into volume 1 and splitting it into volume 2. Okay, so let's just find, using the washer method, let's find volume 1. Okay, so my big R value is the distance from what we're rotating it around to the farthest curve to the right, if we're doing it around a vertical line here. So this distance in pink, that is my big R, we'll call it R1 of Y, right? And then my little r in that same region is going to be this piece that we're going to subtract. So that's my little rectangle there, R1 of Y. So let's find what those actual values are. Big R of Y is going to equal this farthest curve to the right, so that would be 1, and then minus where we end up, 1 minus negative 1. What's the distance between here? 2, right? 1 minus negative 1 gives us 2. That's all you're doing. You're finding the distance between the curves there, okay? That means my little r1 of y is going to equal what? 1, right? Or 0 minus a negative 1, which is equal to 1. Okay, are we okay with both of those distances being 1 and 2? Top curve minus the bottom curve, right curve minus the left curve, okay? So now, R, or big R2, if I drew my big R2 in there, is that going to be different than my big R1? My big R2? Is it different?
No.
No, the big R2 stays the same. It's the little r that's going to change, or that space that we're cutting out, okay? Because now I'm going not to that green line, but I'm going to this blue curve now. Okay, so that is my little r2 of y. Do we see the difference there in those triangles, or rectangles? That's what they are, okay? Wonderful. So big R2 is the same thing. Little r2 is different. So little r2, my top curve or my farthest right curve, is this equation right here, which is that x squared plus 1, right? But if we are integrating with respect to y, what is that curve actually in terms of y? Yeah, square root of y minus 1. Okay, so we're going to take the square root of y minus 1, and then we're going to subtract the the line that we're rotating it about, which is -1. So that would equal, for R2, the square root of y minus 1 plus 1. Let's go ahead now that we have all this information, we can go ahead and write our two integrals that we're going to add together, okay? So my first integral for volume 1 is going to be pi times the integral of big R1, which is going to be 2, so that's 2 squared, minus little r squared, so minus 1 squared. Okay, and for volume 1, we're starting at 0 and we're going to what? 1, right? So starting at 0 and going up to 1. Nothing else is needed to do for volume 1. That is my setup for volume 1, okay? Volume 2, we're looking at pi times the integral of big R2, so that would be still 2 squared, minus little r2, which is square root of y minus 1 plus 1, plus 1 squared dy. Okay, so I've got both of those washers accounted for with those formulas. So if I wanted to write the entire setup for this entire equation, your total would just be those two things added together. I could take a pi out if I really wanted to, so then I would have the integral from 0 to 1 of 2 squared minus 1 squared dy plus the integral. Oh, we forgot to write what we're going to. We're going from 1 to 2, right? Of 2 squared minus square root of y plus 1. Y minus 1 plus 1 squared. So that's your entire setup. If you plug all that into the calculator, that would be your final answer of the volume of that yellow shaded region all the way rotated about the line x equals -1. Same graph yet again. Same shaded region yet again. We are shading this and rotating it now where? Where are we rotating this little yellow section? The line y equals -2. What does y equals -2 look like? Horizontal, vertical? Horizontal at -2, right? So dashed line here at -2. That's where we are rotating it around. So when we draw my representative rectangles in, big R, little r, those are going from the farthest curve to that dashed line, okay? So these rectangles are going to be vertical this time, right? So this is our big R. And then my little r is the part that we're getting rid of. Okay, now if I think about this, do I need two separate pieces for this one? No, because this is always going to be my big R of x, right? And this will always be my little r of x. So there is no need for two here. So we only got one to do, okay? So our formula, are we going to be integrating with respect to x or with respect to y? With respect to x, right? Because we're perpendicular to the x-axis, so we're going with respect to x. So my big R of x formula, this is already in terms of x squared plus 1, right? So I'm taking that x squared plus 1, and then I'm going to subtract where we're going to. So we're going all the way down to what? -2. So this is going to be minus a -2. So if I simplify that, R of x, big R of x becomes r squared plus 3. Yes? My green little r of x is going to start at the x-axis. What is the x-axis value? 0. So we're going from 0, and then we're subtracting a -2, or my distance between 0 and -2 is 2, right? Wonderful. So now that I got those two pieces of information, the only other thing we need to know in order to plug it into my integral is what are my bounds going to be, my lower and my upper bounds. So I'm starting, if we're looking in respect to x, we're starting where? 0 and going to 1. Okay? So my equation for the volume is pi times the integral from 0 to 1 of big R of x squared plus 3 squared minus little r of x, 2 squared. Okay, careful when you're foiling this, right? Or if you can use a calculator, either way, just be careful if you're foiling that by hand, okay? Again, I'm going to save us some time because I know you guys, or you should be able to evaluate this by hand. If you can't, come see me so we can talk about that. But if we evaluate this by hand or on a calculator, we get 36 pi over 5 for your answer. Or whatever that is as a decimal, if you plug the whole thing in, okay? Same picture, last time. Shaded region here. We are rotating it around what line this time? X equals 2. X equals 2 is a vertical or horizontal line? Vertical line, so at x equals 2, I'm drawing my dashed line here. And then we are rotating about that line. Okay, so if I'm rotating about that line, are we going to need 1 or 2 formulas here? We're going to need 2, okay? Because if I look at drawing my farthest curve away from this would be here, right? That distance is using 0, and then once it gets to 1, we're actually going to be using this blue curve instead, right, for our big R of x. Now, our little R of x, does our little R of x change ever for this one? No, little R of x, what we're subtracting each time, so this white distance here, that's always going to stay the same, right? But we are going to have 2 volumes here, so I'm going to label this volume 1, and this will be my volume 2 that we're looking at, okay? So, little color coding here for my rectangles. Big R of x for the first one, we'll call this R1. Now, are we in terms of x or y? Y. So this is R1 of y. And then little r1 is going to be this distance right there. Okay, once we get up to volume 2, volume 2's R2 value is going to change. However, my R, or my little r, I should say, the little r2 is going to stay the same. Oops. So now I got to figure out what are these values actually equal to. So big R1 is my farthest curve minus my closest curve here. So I'm going from this value 2 all the way to 0. So that distance is what? 2, or 2 minus 0, which is just 2, okay? Little r1, that distance is going to be what? 1. Okay. Big R2, we are with respect to y. So this formula is in terms of x, right? Remember, x squared plus 1. So in terms of y, it's going to be the square root of x, or sorry, the square root of y minus 1, right? These are the same things, just written in respect to x and respect to y. So my R2, or my big R2, is going to be the square root. Oh, nope, I lied. Which one's on top? The 2 is, right? And then I'm going to this value. So it's going to be 2 minus the square root of y minus 1. So 2 minus the square root of y minus 1. Or when you're thinking about doing your horizontal slices, it's the farthest right to the farthest left, okay, instead of top or bottom. Make sense? Okay, and then little r2, that's just the same thing, right? Little r2 of y is still 1. That didn't change. Okay, so with those 4 pieces of information, and knowing that we're integrating with respect to y, go ahead and take a minute and write out what your volume formula would be that you could integrate in order to find the volume of this shape wrapped around that line x equals 2. Okay, so volume 1 should be pi times the integral from 0 to 1 of 2 squared minus 1 squared dy. Yes? And then volume 2 is pi times the integral from 1 to 2 of 2 minus the square root of y minus 1 squared minus 1 squared dy. So then my total volume would be V1 plus V2. Okay, and again, just to save us some time, because I know you guys can either do this by hand or in a calculator, and if you can't do one or both of those things, you should probably come see me. But your volume 1 was equal to 3 pi by hand, and volume 2 is 5 pi over 6. So in total, if I add those things together, common denominator, you should end up getting 23 pi over 6 for your volume of that shaded region about the line x equals 2.